I hope you do not get as confused as I do. Alright, we carry on with the chapter on BJT amplifiers. We're going to discuss the common collector amplifier on page 274. If we go and look at the circuit diagram of a common collector amplifier, I hope you still can remember how to identify the configuration. Let me just draw the VCC in here. Remember, VCC for AC acts as a short, so I can see that the collector is connected to ground for the AC signal. But what we've learned is, where is the input connected? The input is connected to the base. The output is taken from the emitter, so this makes it a common collector amplifier, also called an emitter follower. Alright. So you can mark the introductory paragraph there, section 6.4 for the common collector amplifier. Common collector amplifier is usually referred to as an emitter follower. The input is applied to the base through a coupling capacitor and the output is at the emitter. The voltage gain of a common collector amplifier is approximately 1. Now you would ask yourself, what would you do with an amplifier that has a gain of 1? It doesn't amplify, no. And its main advantages are its high input resistance and current gain. Okay, very important characteristics there for the common collector amplifier. Alright, let me just clean this up again. Alright, so if I go and look at figure 625, you can see my small signal still used as an input at the base, but look at the output that is taken at the emitter. Looks very much the same, isn't it? So here I can see, and we will learn very soon why, that the voltage gain is 1. And what is also important is that the output and input signals are not 180 degrees out of phase like the common emitter amplifier was. No. It's because the output is now taken at the emitter. But anyway, let's have a look at the voltage gain there on page 277. As in all amplifiers, the voltage gain is the output voltage divided by the input voltage. And then the capacitive reactances are assumed to be negligible at the frequency of operation. So for the emitter follower, remember this is also called an emitter follower. I can see that V out is equal to IE-RE if I go and look at the model for the emitter follower. And V in is equal to IE in brackets R accent E plus RE. And therefore the voltage gain is then IE-RE divided by IE in brackets R accent E plus RE. The IE current terms cancel, and the base to emitter voltage gain expression then simplifies to RE divided by R accent E plus RE. But please underline this is just above equation 6.12. R lowercase letter e is the parallel combination of RE and RL. Ne? You can see here in this, let me just go to the previous one. Here you can see in this specific amplifier, because the load is connected to the emitter, I can see that RE and RL is now in parallel. Alright, so I have to go and calculate the value called R lowercase letter e. Okay, so remember that. Okay, and then if there is no load, then of course R lowercase e is equal to just RE now, because then I can't calculate RL in parallel with RE. And we also know if R accent E is much smaller than the value of RE, rule of thumb normally 10 times, then I can leave out the value of R accent E. So then I can assume then that the voltage gain is RE divided by RE, which is going to be 1. It's never going to be 1 exactly. It's going to be close to 1. It will always be less than 1 because of the value of R accent E. You understand that? No. Alright. So we make the assumption, because R accent E is very small, that the voltage gain is equal to 1. Does it make sense? Alright. So, now you can mark this paragraph as well. It says, since the output voltage is at the emitter, it is in phase with the base voltage, so there is no inversion from the input to the output. Because there is no inversion and because the voltage gain is approximately 1, the output voltage closely follows the input voltage in both phase and amplitude, thus the term emitter follower. Alright. So remember, common collector amplifier, also called the emitter follower, exactly for this reason, as we've seen now that the voltage gain is approximately 1. Always less than 1, but we assume it to be approximately 1. Alright, everybody happy with that? Alright, let's carry on. Input resistance. Now this is another characteristic that you have to remember, so please mark this. The emitter follower is characterized by a high input resistance. This is what makes it a useful circuit. Because of the high input resistance, it can be used as a buffer to minimize loading effects when a circuit is driving a low resistive load. Now can we already see where we are going? The previous amplifier that we've discussed, the common emitter amplifier, what was the problem there when I calculated voltage gain? Voltage gain was equal to maximum voltage gain. It's RC divided by R accent E, but we saw I couldn't use that. I had to use swamping to make it more stable, so it was R accent E plus RE. If R accent E was small enough, it was just RC over RE1. But that RC, as soon as there was a load resistor, I had to calculate R lowercase c, which was RC in parallel with RL. Now what was my problem with a normal audio amplifier? If I want to use this as a normal audio amplifier, what is the resistance of a speaker? 8 ohms. Now you can imagine, say for instance RC was equal to 1 kilo ohm, and I've got an 8 ohm resistor and I have these two in parallel. What's going to happen to RC? It's going to be less than 8 volts. Close to 8 volts, less than 8 volts. What's going to happen to my voltage gain? That's going to go way down. Alright, so here I can already see, but we will discuss it just now. Don't worry too much about it. I'm just letting you start to think about this in the meantime. Okay? Because I see here, because of the high input resistance, it can be used as a buffer to minimize loading effects when the circuit is driving a low resistive load. Take note of that. Alright, then they say the derivation of the input resistance looking in at the base of the common collector amplifier, similar to that of the common emitter amplifier. In a common collector circuit, however, the emitter resistor is never bypassed. Underline. Okay? Because the output is taken across RE. R lowercase e, because that's R in parallel with RL. So RE is never bypassed in a common collector amplifier. Alright, then there's a derivation by using Ohm's law and substitution and so forth. But you can see right in the end, R in at the base is equal to beta AC R accent E plus RE, the same as we've had with the common emitter amplifier. And then finally, we also said if R accent E is much smaller than RE, I can assume that R in at the base is equal to equation 613 beta AC times RE. Alright, so and I also have to calculate the total input resistance then, the same as for the common emitter amplifier. R in total is equal to R1 parallel with R2 in parallel with R in at the base. Alright, so that's the input resistance, and we've seen that it's characterized by a high input resistance. Alright, the next point there is the output resistance with the load removed. the output resistance looking into the emitter of the emitter follower is approximately equation 614. RS divided by beta AC in parallel with RE, where RS of course is the internal resistance of my source. Now they say here the derivation of this expression is relatively involved and several simplifying assumptions have been made as shown in Appendix B, but we're not going to discuss that. But you can underline this: the output resistance is very low, making the emitter follower useful for driving low resistance loads. Can you see again here? That's why they say I can use it as a buffer. We will discuss it now. I will use this amplifier as a buffer between my common emitter amplifier and my low resistive load, my 8 ohm speaker. Alright, so you can see this is ideal for a low resistive load, 8 ohm speaker, but we will discuss it now. I'm just making you think about it in the meantime. Alright, the next point is the current gain. The current gain is IE over I in, where I in is V in over R in total. And lastly, the power gain is going to be equal to the current gain, of course, because we've seen that the voltage gain is approximately 1 now. So I can still say power gain is equal to voltage gain times current gain, but voltage gain is equal to 1, so you might just as well say that the power gain is equal to the current gain. Alright, so that is the comparison of the common collector amplifier to the common emitter amplifier. Common collector amplifier also called the voltage follower. But let's have a look at example 6.9. The example or the question asks, determine the total input resistance of the emitter follower in figure 627. Also find the voltage gain, the current gain and the power gain in terms of power delivered to the load RL. Assume that beta AC is 175 and that the capacitive reactances are negligible at the frequency of operation. You will see in a later later chapter that we're going to do, it's not actually true, but for simplicity's sake we assume it at this stage. We will discuss frequency influences in another chapter. Alright, but don't worry about it now. Alright, so if I go and look at the solution, first I go and look at the amp, I can see, fine, this is a common collector amp, input at the base, output at the emitter, so it's a common collector or also called an emitter follower. Now the AC emitter resistance external to the transistor, remember there is a load resistor, so I must determine RE in parallel with RL to find R lowercase e. And in this case I got 235 ohms. The approximate resistance looking in at the base, they say approximate because they don't use the value of R accent E at this stage. R in at the base, beta AC times this RE that I've just calculated, 41.1 kilo ohms. Then I can calculate the total input resistance. R in total, of course, then R1 in parallel with R2 in parallel with R in at the base, same as we've done for the common emitter amplifier, 10.1 kilo ohms in this case. We also know that the voltage gain is approximately 1. I assume it to be 1. But by using R accent E, you can determine a more precise value of the voltage gain if necessary. So let's do it. I will calculate VE in this case now. The voltage divider formula, R2 over R1 plus R2 times VCC minus VBE. That's why I'm calculating VE. I'm subtracting the 0.7 volts already. And then I have a value of 6.69. Why do I want to calculate VE? Because I want to determine IE. I need IE to calculate R accent E. Alright, then IE 14.2 milliamps, R accent E 25 millivolts divided by that IE, get a value of 1.76 ohms. So I can go and count the precise voltage gain, and I can see then if I include R accent E, the actual value is 0.992, which is very close to 1, but it's not 1, and it will always be less than 1. Okay, the small difference in voltage gain as a result of considering R accent E is insignificant in most cases. The current gain is equal to IE over I in, and I do the calculation as follows. IE is equal to VE over RE, lowercase letter that we've calculated now. Then I say it's A voltage gain times VB divided by RE. I substitute the values there, and I get an answer of 12.7 milliamps. I in, of course, is V in over R in total. 297 microamps. Ladies and gentlemen, please take note again. Can you see that this value is very small? 297 microamps. So accuracy is very important. Calculate all your answers that you calculate accurate to 3 decimals, and you have to express it in engineering notation. You've learned how to do that in electronics 1. Is that true? So please remember, you cannot write for me that this is 0.297 milliamps. It's not engineering notation, eh? 297 microamps is the answer. Alright, then I can calculate the current gain, IE divided by I in, 42.8. Remember that these gains are ratios, they haven't got a unit. And then, of course, the power gain will be exactly the same, more or less the same, because we've seen that the voltage gain is very close to 1, actually 0.992. No? Alright, so since RL is equal to RE, 1/2 of the power is dissipated in RE and the other half in RL. Therefore, in terms of power to the load, the power gain is divided by 2 for the load resistor, because those two values we can see that RE and RL have the same values. But if they aren't the same values, I'm sure you're very good with mathematics, you will be able to calculate the weight that it carries, the amount of power that it will carry. Alright, but the next section, also NB, very important for this type of amplifier. It's called the Darlington pair. Now, seeing that it is Valentine's Day, it's not you and your girlfriend or you and your boyfriend, this Darlington pair. This is something else. This is Sidney Darlington that lived from 1906 to 1997. He was an electrical engineer. But anyway, important here is that as you have seen that beta AC is a major factor in determining the input resistance of an amplifier. Every time it's beta times resistance. So beta is a major factor. So the beta AC of the transistor limits the maximum achievable input resistance you can get from a given emitter follower circuit. Alright. So how can I improve this? One way to boost the input resistance is to use a Darlington pair, as shown in figure 6.28. The collectors of the two transistors are connected, as you can see. And the emitter of the first drives the base of the second, and the configuration achieves beta AC multiplication, as shown in the following steps. So what is going to happen if I connect the transistors in this fashion? Remember, say for instance beta AC was 100 and I had a 1K resistor, so my input resistance would be 100 kilo ohms. But in this case, beta AC is multiplied with beta AC2. Beta AC1 is multiplied with beta AC2. So it's 100 times 100 times the resistance. So you can see the input resistance will get much bigger. But follow there in the book. The emitter current of the first transistor, IE1 is equal to beta AC1 times IB1. The emitter current becomes the base current for the second transistor, producing a second emitter current, IE2, which is beta AC2 times IE1. So I can see then that this is equal to beta AC1 times beta AC2 times IB. So the effective current gain of a Darlington pair is beta AC1 times beta AC2. So neglecting R accent E by assuming that it is much smaller than the value of RE, the input resistance now becomes Rin, which is equation 617, just above figure 628, beta AC1 times beta AC2 times Re. Ne? Okay, you have to know the Darlington pair. Why is the Darlington pair used? And you also have to be able to draw the Darlington pair as well. No, recognize it. Okay, now I've been hinting at this application right from the beginning of this section. And the application as in the books there you can see figure 629, a Darlington emitter follower used as a buffer between a common emitter amplifier and a low resistance load such as a speaker. Okay, so in the previous section, this is what we've discussed, né? This section here is a partial diagram of a common emitter amplifier, as we've discussed in the previous section. The next section over here you can see is my Darlington emitter follower. No, it's a emitter follower, it's still a common collector amplifier, but I'm making use of a Darlington pair. Why do I do that? To boost the input resistance. No? Why do I want to boost the input resistance? Because we've seen for this amplifier, the common emitter amplifier voltage gain is equal to R lowercase c, eventually if there's a load resistor, over R accent E actually plus RE1. Ne? There should have been swamping applied to this to amplify to make it more stable. Now you agree? Alright, but my problem lies over here. Because this R small c is equal to RC in parallel with RL, and we've seen if this RL is only 8 ohms, my RC becomes quite low and my voltage gain is going to be very small. Now if I use this emitter follower or the common collector amplifier as a buffer in between, we've seen that the input resistance is high, especially if I use a Darlington pair. Rin is equal to beta AC times beta AC1 times beta AC2 times Re. No? High resistance, so what happens? I don't have a low resistance in parallel with RC anymore for my common emitter amplifier. No? So that's a high resistance then. And if I have a high resistance in parallel with another high resistance, I will still have a high resistance and my voltage gain will not be influenced. Alright, so for my common emitter amplifier that will be fine. But what have we also seen for the common collector amplifier or the emitter follower? Ideal to drive low resistive loads. Nah. Ideal to drive low resistive loads. So I use this amplifier as a buffer. A buffer between my common emitter amplifier and my low resistive load. So that I can still have the voltage gain that I was hoping for when I designed this amplifier. Does it make sense? But please read there in the books. All of this that I've explained to you is written there underneath application on page 280 and on page 281. It's exactly what they explain there. They show you by using values such as the 8 ohm resistor, what does RC become? The 8 ohm in parallel with the 1 kilo ohm becomes 7,94, very close to 8 ohms still. But what becomes of my voltage gain? Without the load resistor of 8 ohms, my voltage gain is 200. That's when I'm not using swamping, of course. And if I have a load resistor, even that 200 becomes 1,59. You see how huge the influence is of a low resistive load is to the common emitter amplifier. But of course, all that is remedied, rectified by using the emitter follower amplifier as shown in figure 629. Clear to everybody? Please read through that and work through example 6.10. It's just doing this by using some values again. I can just point out perhaps Let's read the question quickly. In figure 629 for the common emitter amplifier, VCC is 12 volts, RC is 1 kilo ohm, R accent is 5 ohms. For the Darlington emitter follower, R1 is 10 kilo ohms, R2 is 22 kilo ohms, RE is 22 ohms, RL is 8 ohms, low resistances, nee. VCC is 12 volts, beta DC is equal to beta AC is equal to 100 for each transistor. Then you have to go and determine the voltage gain for the common emitter amplifier. You have to determine the voltage gain of the Darlington emitter follower and determine the overall voltage gain and compare to the gain of the common emitter amplifier driving the speaker directly without the Darlington emitter follower to draw the comparison. But anyway, what I'm trying to point out here in the solution, if you go look there where VB is calculated, they calculate R2 in parallel with the input resistance. Now, the input resistance, remember now I'm using a Darlington pair. I'm not going to calculate the input resistance, I'm going to use it. Okay? In this case, you can see it's beta DC squared. Why is it beta DC squared? Because both transistors have the same value of 100. Now. Okay, so that's the only reason. It's not a funny formula or something. All right. But anyway, work through that. Make sure I want to leave this specific one for you to work through. I want to be sure that you understand this. Okay. So when we get together again and the homework is done for this section, I want you to ask if there's something that you don't understand. Alright, just after that example on page 282 is another device. It is called the Zickley pair, figure 630. It's similar to the Darlington pair except that it consists of two types of transistors, an NPN and a PNP, as I can see here. No? There's the PNP, there's the NPN. The configuration is sometimes known as a complementary Darlington or a compound transistor. Just remember those alternative names also for a Zickley pair. Complementary Darlington or a compound transistor. The current gain is about the same as for the Darlington pair. The difference is that Q2 base current is the Q1 collector current instead of the emitter current, as in the Darlington arrangement. The next paragraph you can mark some advantages and disadvantages for some nice theory questions. An advantage of the Zickley pair compared to the Darlington is that it takes less voltage to turn on because only one barrier potential has to be overcome. A Zickley pair is sometimes used in conjunction with a Darlington pair as the output stage of power amplifiers. In this case, the output power transistors are both the same type, two NPN or two PNP types. This makes it easier to obtain exact matches of the output transistors, resulting in improved thermal stability and better sound quality in audio applications. Just an alternative to the Darlington pair also used, so be aware of that circuit as well. Okay, this concludes the section then on the common collector amplifier. Again, same as always, don't get bored with what I'm writing here at the end. Read through the section discussed, very important. Do the examples and the true-false quiz, circuit action quiz and self-tests. And at this stage you have to do basic problems 20 to 25. So you can see how it becomes gradually more and more and more. No. Don't fall behind. Because if you're going to fall behind, you're going to fall out. Are you going somewhere?